Od obnoviteľných zdrojov cez jadrovú energiu až po fúziu. Veda nás obklopuje všade okolo nás. Vítajte pri špeciálnej starmusovskej epizóde Vedátorského podcastu, kde nie je Jozef, lebo bol chorý, som ja. Rozprávam sa s profesorom Chuom, ktorý dostal Nobelovú cenu za fyziku, ktorý sa venoval energetike a ktorý má veľmi zaujímavé predpovede o tom, ako bude budúcnosť energetiky vyzerať. Neprekvapivo je táto epizóda v angličtine, takže ak máte s angličtinou napríklad problémy, tak si môžete epizódu pustiť na YouTube, pustiť si titulky a čítať si, o čom sa rozprávame.
Usually we are recording in a studio and there is somebody taking care of this, but as you might have noticed, STARMUS is very fluid and changing very rapidly. So
yes, I noticed.
So we'll have to improvise a little bit.
Right.
So in one of our episodes, our listeners can send questions to us. Mm-hmm. One of the questions was about lasers. Mm-hmm. Usually you use lasers to heat something up, to melt something. Mm-hmm. But it's also possible to use lasers to cool something down, which is completely counterintuitive. And there isn't a better person to explain how can this work than you. So can you explain how you can use lasers to cool things down?
Okay. So the first thing your listeners have to realize is that light carries momentum. And this is embedded in the most fundamental equations in classical electricity and magnetism. But then we later learned there's an alternate way of describing light in terms of particles of light. But each particle has a certain amount of momentum. Mm-hmm. Just as each quanta or particle of light has a certain amount of energy. And then in special relativity, energy and momentum are very related. So imagine you're an atom, big atom, bowling ball, okay? And the particles of light have tiny momentum, little BBs bouncing off this bowling ball, So bowling ball is rolling towards you, and you're shooting little BBs, beep, 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 at us. So many, photons, and the bowling ball will slow up. How many photons? Well, hundreds of millions of times a second. Okay, but here's the problem. The bowling ball is going towards you, so you know where to aim. Mm-hmm. If the bowling ball is going away from you, you're going to speed it up. That makes it hotter. But temperature is random motion. So these atoms are going backward, forward, every which way, sideways. So how will you know? So then you use another trick. And the interaction of light with the atoms has frequency dependence. There's a frequency you tune to that maximizes the scattering of the light. Now you tune it off resonance a little bit. So the atom going towards you, or the bowling ball going towards you, there's a thing called Doppler shift. So in the frame of reference to the atom, as you walk towards this source of light, it looks a little bit higher in frequency. And if you're walking away from the source, it looks a little lower in frequency. Okay? So now, atom going towards you, more in resonance, more BB hits. Atom going away from the other light beam, it's running away, out of resonance, fewer BB hits. So it becomes automatic. No matter which way the atom goes, forward or backward, doesn't matter. You just are slightly tuned off resonance and use what we call as the Doppler shift, that change in frequency. And it worked.
So it brought some order in the chaos.
Yes. And so then it's a very important question. So where does the energy go? Because the photon just moved, okay? But on average, if you look at what's happening, the photons that get scattered are a little higher in frequency than the photons not, okay? So it's a little bit more energy in the light. So you're transferring the energy, the moving energy of the bowling ball, the atom, into the light. And similarly with what we call the disorder, the so-called entropy.
Yeah, because for me, the energy wasn't the tricky part. It's always conserved. The entropy was the tricky part. So
yes, entropy. So to your readers, what is entropy? Entropy is the number of accessible states. Imagine you have these laser beams, very well ordered. Okay? And then they're everywhere. So photons going in a very orderly manner, left and right, top and bottom, forward and backward, are now spraying out everywhere. So the number of accessible states has increased.
In a very similar fashion, can you use lasers to split black holes? In the same regard, like you will pump energy and make it split into two if you pump energy enough so the entropy horizon could decrease?
Okay, I'll be honest and say I don't know, and then I'll put a little forward and say I severely doubt it. It depends. Most of the black holes we know are very big. There are a few solar masses, 2 millions of solar masses, at the center of galaxies. And we don't have powerful enough lasers. And I don't even know if it can be done because these black holes just swap the photons. And they just get more massive.
Whenever I hear about some high energy phenomenon, this is high energy at least from human point of view, lasers is high energy. I ask myself if this has some counterpart in early universe. Can this be applied somewhere in the early universe, like ordering things, cooling things down in a similar way by this tuning with help of Doppler shift?
So the current view of the universe, including the early universe. So inflation and everything may be true, may not be, very speculative. But this much we know for sure. That at the very beginning, the universe was expanding very fast. And so the light is being redshifted from gamma ray and even higher. And so then there are two things that happened. One is that at the beginning, when everything was a soup of quarks and this and that, lots of high energy, that we were very coupled to electromagnetic radiation, and charged particles interact with electromagnetic radiation very strongly. And then when atoms start to form and become neutral, then the interaction went way down. So if you have charged particles, radiation levels, and being neutral, it's only very fine energy levels. Okay, so this is the decoupling of light from matter, and that occurred at a time long ago. And after this decoupling, the universe is expanding. As it expands, the current view of the universe now is that it's space and time expanding. So if space and time expand, imagine electromagnetic radiation or a photon. Let's say electromagnetic radiation, it expands. The wavelength gets longer, the frequency gets longer, the frequency goes lower. So it goes from very high energy gamma rays to radio frequency.
Something safe.
And so this microwave background radiation that was discovered and got a Nobel Prize was a glimpse of an early universe, but not that early, where you can see these things. And then theoretical physicists are saying, well, if you can begin to measure the polarization of the light, then you can try to back calculate what was happening in the earlier universe, and inflation has some suggestions of what that might be. Very hard measurement, so they're trying to do that. Neutrinos decoupled sooner as they interacted, but it's very hard to detect enough neutrinos to do cosmology. So to get a glimpse of the earlier universe is very difficult because the light turns out to be so far our best vantage point.
So we're trying to see some order in the early universe.
Okay. So now it's very interesting. So the discovery of the black body radiation first got a Nobel Prize, the Penzias and Wilson at Bell Laboratories. There was another Nobel Prize. What was for black body radiation given to some people? One was, is it black body radiation? Black body radiation is, you think, black. How can there be radiation? Okay. And so first let me describe what black body radiation is. Suppose you have a hole in this big cavity and you're looking at light and light impinging on the hole. So it goes in the hole, never comes back because it rattles around this big volume, just scattered. Okay. Black. Okay. No reflected light. But this big hole has a temperature, some finite temperature. Because it has finite temperature, we know we can calculate what the radiation spectrum is. That was one of the early triumphs of quantum mechanics. It was Planck who said you use classical E&M and you get the wrong answer. And he says, well, if you say there's a minimum energy that this, but he said it's fictitious, but never mind.
He wasn't happy about the interpretation.
He didn't like the interpretation, but it gives the right spectrum. If something is a certain temperature, he gives a distribution of light at different frequencies. That light is, remember, the whole is our surface. And light comes from inside and comes out. So black body is a perfect absorber and a perfect emitter. Okay? So we think we understand black body. Now here's what's really interesting. Another Nobel Prize. How close to black body is it? It is, as near as we can tell, perfect. It's the perfect black body. There's no other experiment we can do on any other black body that
works so well.
That works so well as black body. Now, another weird thing. The spectrum of black body here, on this side, looking back billions of years, and the spectrum looking back billions of years, separated, right? The universe is expanding, it's evolving, right? But once special relativity says something over here can't talk to something over here, separated by, let's say, 20 billion light years. And yet the black body spectrum is good to 5.5 decimal places, same temperature. What's going on? So then you have to invent something new, that there's such a rapid inflation that really got the universe to where it is today. So it didn't have time to evolve. It didn't have time like Australia being separated from the continent, and you have weird evolution of, platypuses and koala bears and kangaroos. Okay, those animals are very different than South Asia, right? Okay, so we just invented something. We said, oh, there's this rapid inflation. What caused it? Well, we don't know. We can make a mathematical model of it. And, it's when the universe is formed, it's at some unstable point. It's like a pencil balance on the tip. You let it go, and it can fold to left, it can fold forward, backwards, okay. And it folds down into a lower energy. But which way it folds in lower energy can be anywhere. So it shows some random thing. That's where we are. So now, believe it or not, this also is beginning to have experimental tests, the inflation model. And I go back to the polarization of black body radiation, then we can start testing some of this. Is it true or not? Which is the only thing that separates science from philosophy or religion. You have to be able to falsify a statement. You can't prove something to be true, but you can prove something to be not true. And so this is the basis of science and of quantitative knowledge. So very exciting. We don't know what's going on. Now we know the universe expanding, but of course you can have two scenarios. It's expanding a little bit too slowly, so self-gravitation brings it all back together, so the universe collapses. Another scenario, it's expanding and it's expanding just perfectly so that time equals infinity, everything stops. Or it's expanding too fast and just everything just keeps on going. Okay, then, so scientists set out to study which is it? It was neither. The universe is expanding and it's picking up speed.
Yeah, that was a big surprise.
Big surprise. The sign was wrong. So what's going on? We don't know. Einstein, in his theory of general relativity, he knows something, that this is, you have a moving universe, but at this time he thought that the universe was stable and not doing anything. So he sticks in a little parameter in his equations in general relativity and says, okay, now we have a stable universe. And then they discover, Hubble and others, that the universe is expanding. So this Einstein constant Einstein's his biggest mistake in my career, okay? Because now we know from observation the universe is expanding, but got the wrong sign. Well, you can use that parameter and say, well, we can adjust anything we want so it can get the right sign. It's expanding. Now, that's just a parameter in an equation. We don't know what it really means. And so we called it dark energy. It makes sense because one of the discoverers of this dark energy, the expansion of the universe, and acceleration, worked in Department of Energy Lab. So,
You offered me here a nice way to pivot, because when someone opens your Wikipedia, the Nobel Prize is at the end of paragraph. The first part is about energy department working in Obama's administration, and you are one of the probably world leading experts on energy, on the future, and so on. So I'll ask you 3 consecutive questions. The first is, how will the energy of human population look at the end of this millennium, this century, and this decade? So just to set up, the long-term, mid-term, and short-term future.
You want me to go long-term first?
Yeah, long-term. So let your imagination run wild.
Long-term. We can probably figure out how to make energy from fusing tritium and deuterium together. When you fuse these 2 isotopes of hydrogen together and form helium, the nuclear binding energy of the helium is you release a lot of energy, because you have these 2 parts and they attract each other. You get something more stable, so there's extra energy. That extra energy is enormous. If you look at the amount of energy per nucleon, what you gain from fusing tritium and deuterium together is huge, much, much bigger per unit mass than splitting uranium into lighter isotopes. It has another advantage in that the reaction is inherently not radioactive. Helium is a very stable isotope. Now, there are some problems. The problems are when you fuse this, you make neutrons, high-energy neutrons, okay? 14 MeV neutrons. And these neutrons go into material, and they knock the nuclei on this material around. They're neutrals. They don't see the electron cloud. They go straight from the nuclei. A momentum transfer, so the nuclei move around. Maybe 10 to 100 times a year for commercial neutron magnetic confined reactor. Not ITER, it's low flux. No, not anything we're close to seeing. But if you want to go commercial, you have huge neutron damage. In addition to that, these neutrons create helium. Helium is a gas. And so the material starts to crumble because you're moving the nuclei around and you're making helium. So think of this metal as turning into a crumbly Swiss cheese. So it falls apart. We do not have a solution yet, the material solution. Okay, until we can get materials that will last, not 5 years, not 20 years. The new nuclear reactors are being built for 80 years.
Wow.
The original licensing was 40 years, but it was very conservatively designed. And in the United States, virtually all the nuclear reactors are being now relicensed for 60 years. Japan, after Fukushima, they were going to 60% nuclear, and then Nope. Goes zero, and then they realize, they have to build coal plants. This is really bad for climate. So they're bringing back nuclear. Okay. Designing for 80 years. Our nuclear-powered submarines, okay, they're refueled once, but it's a big pain to refuel a nuclear-powered submarine. You got to take the submarine and split it open. So next generation nuclear-powered submarines, no refueling, 60 years. But that's different because the uranium they used is 95% U-235. This is the stuff you make bombs with. Commercial reactors have to be below 20% or below. Conventional nuclear reactors today refuel in 2 years. The newer generation, especially the small modular reactors, can go for 10, 20 years. Mm-hmm. So it's like a battery. You build in a factory, you ship it out there in a truck, you use it for 10 or 20 years, you ship it back, and we ship a new battery. Mm-hmm. Okay, so this is technically possible. We have to learn how to make them cheaply. The economy of scale of making 1 gigawatt electric power to 1.6 gigawatt electric power, you just make them bigger and bigger. When you make them smaller, it costs far more per unit electricity, so you make up for it by making thousands of them, exactly the same, all at once. And so that's the promise, and there are numerous countries and a bunch of companies try to do this. But fusion does make radiation. It's called neutron activation. So when the neutron slam is, the neutron activates them. And so you do have radioactivity, but that radioactivity is much shorter lived. We have a materials problem. So right now the design is you've got to have a lithium. It used to be liquid lithium, but then liquid lithium, very corrosive. So I said, can't. So nanoparticles of lithium that don't corrode, that absorbs as many of the neutrons as possible. So you make tritium. Mm-hmm. We don't have enough tritium to turn on ITER. This is not widely appreciated. And ITER is just an experiment. And so we need to get more tritium and breed more tritium. So you have to bootstrap. Which came first, the chicken and egg? Well, we need both. Mm-hmm. So we have a materials problem. We have a tritium problem. Tritium problem, I think we can maybe solve, if you're patient. The materials problem, we have to solve. Otherwise, it goes nowhere commercially. Okay. But 1,000 years from now, sure, we will figure it all out.
So isn't that the end of century for fusion?
I personally think, and we're now talking wide-scale deployed fusion. You talk to people, and I think the President of the United States said in 10 years or something, but he doesn't, he's not a scientist, but he's listening to Secretary of Energy. Secretary of Energy used to be governor of Michigan. She's not a scientist, okay? Mm-hmm. So she made this announcement. The scientist, what? Commercial is very different than an experiment. Mm-hmm. Commercial means you have to make it on time, on budget. The cost, of the first 10 will not be $10 billion. Well in excess, tens of billions of dollars. You're over budget, you're dead.
So it's like comparing private flights to moon and scientific mission, which was very, very expensive.
You're exactly right. Apollo mission to moon, buy a ticket to do a little tourism. That's commercialism, okay? And so when will commercial be widely deployed? Even if you put a first reactor that's breaking even and generating more energy than it uses, that could be 20 years, but it's not. It's like Apollo.
But it will be the perfect source of energy, so we don't have to look no more for something.
That's right, because there's a lot of deuterium. You can breed tritium. The reactivity is very short-lived. Mm-hmm. Hundreds of years. Well, 100 years we can deal with. For nuclear reactors, the longest isotopes are millions of years, but then some of those isotopes really can get into the environment, into biological systems. So there's a danger with nuclear waste. You've got to dispose of it. with fission, it's okay. So 1,000 years, we're smart. We'll figure out fission.
So then
Fusion.
Yeah, that's a common mistake. So if at the end of century it isn't fusion, it's fission and renewables or mixture, or depending.
It's going to be a mixture. I mentioned in my talk that we looked in the United States. We made a transition from wood to coal to oil and gas. And gas is so plentiful in the U.S. because of this technology of fracturing rock and horizontal drilling. And we know how to do this very well. We actually know how to do it without having this gas leak out. But, you know, some of the people who are against everything think that fracking's terrible. If done wrong, everything can be terrible. Okay. So it will be a mixture. We need some compact turnout sources. Not everywhere can have pumped hydropower, lifting water up a hill. So it's potential energy which you can recover. Can be very efficient. 30-meter dam, be over 70% efficient, 75%. Great. So not every place has mountains. Places do have mountains. Switzerland tapped out. No more hydro. Norway nearly tapped out. No more hydro. Okay. Austria can make some more dams, but very few countries. But a lot of people don't like dams because it's against nature. So is climate change, but never mind that. So it's going to be a mixture of wind and solar. Solar is going to get much, much cheaper. Mm-hmm. I think we will master perovskites to make them last 30 years. And as I mentioned, the thickness of a perovskite is 300 nanometers, not 150 microns. And you can alloy them differently, so you can stack them. So two-layer of perovskite plus silicon or two perovskites, you're going to 30% efficient. The polysilicon solar cells are about 18% efficient. Single crystal, commercial single crystal is about 21%. The stuff that NASA puts up, silicon, the very highest grade, is 24%. Okay?
So at the end of century, what percentage can we expect?
35% thin film. We have to develop. Okay, so silicon, the cheapest substrate is glass. It remains glass. It's very durable. Glass is heavy. NASA doesn't put up glass, and okay.
Very small windows.
And so we need to develop polymer, thin film polymer, that takes advantage of this 300 nanometer, and you have layers. But we have to make it so it's UV resistant, which we don't know how to do yet. But that is solved.
We have a century for that. So.
Yes, we have a century. So I think perovskite, multi-layer perovskites will take over. Mm-hmm. They used to only last months. Now they're less than 15 years of accelerated life testing by exposing more sunlight radiation. That was a year ago. I think in a couple more years, we'll get it up to 20, 30 years. Okay, so price of solar goes down. The weight and the efficiency means all the other stuff goes down, the so-called balance of systems. Wind is going to get better. They're getting better because they're getting better engineered. They're going from 5 megawatts to 15 megawatts per turbine. These are very, very big. And they're so big that the nautical, where the blades are attached, are little helicopter landing pads now.
At some point, people will be living in the cylindrical part.
So this is just engineering, but it's getting better and better and better. And so I think wind and solar will get better. We have to learn how to build better transmission lines. After a certain voltage, it doesn't make any sense because of corona discharge. So the Chinese are building have built and installed 1.1 million volt DC. DC is better than AC. Why? Because of the radiation. Even though it's 50 or 60 hertz, You have loss due to radiation, you have loss due to conductivity, and then you'll have loss due to the fact that the oscillating field couples to the Earth, which is a bad conductor, so you lose radiation that way. You cannot make an underground cable AC for very long because you're coupling too much energy into the ground. And so you will want to make higher voltage DC voltage. So we learn in elementary physics that the loss, the power going through is the current times the voltage. The loss scales as voltage squared over the resistance. Okay, meaning the inverse of that. So you go to higher voltage, double the voltage. You can put in V squared over R, yeah. So same power at lower, for the same resistance, you quadruple the power generated. You make it higher, you can go even higher. But you stop when corona discharge takes over. The standoffs of 1.1 million volt is about 1 story in distance. And so that's probably near the end of the limit. They were going to build 1.3, but I think they said, no, 1.1 is good enough. 3,000 kilometers. So we need to build better dielectrics to make undersea cables or under the river cables. You can, with DC, you can put about 2 or 3 times more power in a DC line from the same tower. So people are beginning to replace, for the transmission towers, the AC lines with a few DC lines. It costs a lot of money in electronics to get it up. How do you get voltage up that high? You turn a high-frequency alternating current and use transformers. Higher frequency, smaller transformer. The power electronics needs more development. So when I was Secretary of Energy, I was investing in ways to make the wide band gap. So we go from germanium to silicon, to gallium nitride, to silicon carbide. The best is diamond. Huge band gap. Huge thermal conductivity. Perfect. But we don't, and we can dope it one way with boron, but we don't know how to dope the other. So you can't make a bipolar transistor with diamond yet.
So is that an issue of price, but physics?
Everything in energy is price. Everything. But we know how to make diamond CVD cheaply. So that we know how to do. So it's a materials question. And if you heard my talk, I said, materials is the enabling technology. Neutron damage will prevent a commercial fusion. So we have to fix that. It's a materials problem. Wide band gap diamond transistors, a materials problem. I go down the list and all I see is materials problems. And you solve the material problems, right? So about 100 years, maybe we solve that. How long have people been working on diamond transistors? 30 years. Let's see, transistor was invented in 1948. So at least 30, probably 40 years.
So this all has a very huge momentum. So what can we expect by the end of decade? Because 5 years ago, I would say things can change very, very slowly only. But then after the Russian invasion to Ukraine, Europe changed rather swiftly and made huge changes in 2 years maybe. So can we expect huge changes by the end of this decade, or it was just one very big jump? And
I would say one of the biggest stimuli for rapid change is war. One of the biggest stimuli for technology change is war. I mentioned Bessemer steel process during war. Okay? Airplanes. Look at airplanes.
radio technologies.
Radio technologies all leap forward during war. First World War I, then World War II. U.S. Wright brothers invented airplane December 1903 or 4, something like that. Man and Moon, 1969. But it lurched forward, aircraft lurched forward during World War I. By that time, the Europeans made better airplanes than the U.S. by 1914. Mm-hmm. So we know, but America was a good factory. And so the French and British said, don't make airplanes. We make better planes. Make our planes. And we agreed. Mm-hmm. They made better planes. World War II, leap forward, right? The first jet planes out of World War II in Germany. And so all this technology leaps forward during war. And then the other thing we learned in the war in Ukraine was that Russia is not a reliable partner. Russia had infiltrated Germany for decades, convincing the small towns that nuclear is bad, it's dangerous, and will supply you with gas. So Germany didn't really have an energy plan to get carbon-free. Their plan was just import cheap Russian gas, and we don't need nuclear, and so they shut down all the nuclear reactors.
Terrible mistake.
But it's because of this infiltration and brainwashing by the Russians over decades. And so
still a terrible mistake. Yeah.
Still a terrible mistake. I did my best to try to convince Germany. I advised Helmholtz energy programs, 5 billion euros a year. Got 6 years as advisor. They put me forward to German parliament. You don't want to do this. You do this, you will build coal plants. I said, no. We'll do wind and solar. They build coal plants. So what is going to happen?
What is decade?
Okay.
So hopefully no big changes by the end of the decade.
Okay. I think EVs in 7 years will become significantly less expensive. They have to be. The batteries have to charge faster. Takes too long. The best, fastest charging Teslas can go 200 miles in maybe 20 minutes. Okay? So people are doing research in batteries that may be 200 miles in 6 minutes being tested now.
Okay.
So I go around giving talks. The goal is the battery has to last longer than the bladder. So if you're on a long trip, you're not going to drive more than 200 miles. You want to have a rest stop. You want to go to the bathroom. You're discharging your car's charging 4 or 5 minutes. You don't care. The service station loves it if you spend 4 or 5 minutes. Why? Because they make much more money from soda and TVs and cigarettes than from selling gasoline.
Wow.
I know this because I'm advised Royal Dutch Shell. They own their gasoline stations. And they said the profit is on selling this stuff, not selling gasoline. The gasoline margin is razor thin. Internal combustion engine cars, profit margin razor thin, where they make the money from maintenance. So the car dealers hate this because electric vehicles have much less maintenance. Okay? But as soon as the vehicles can charge 5 minutes, 200 miles, cost the same, the operating costs far less. And then by that time, in 10 years, there'll be a lot of green electricity, no longer from coal, and as the years go by, even better. So I think that will happen. That's good news. There's progress being made in high voltage DC transmission. Good news. Wind and solar are going to get at least twofold less expensive. But if perovskites happen, much less. Because of the shipping, the weight, the handling, if you can roll out plastic, it becomes, and double the energy per unit area, because you need a lot of land for solar. With wind, but some people hate wind turbines. U.S. farmers in the Midwest, they love them because they get income every year. They get more income from renting their land for a wind tower than they do planting crops. It's like gasoline stations selling magazines and cigarettes. And so even very conservative right-wing Republicans don't mind wind because they make money out of them. So all these decisions are all about money. So I see these are good bright spots. Okay? EVs, cleaner electricity, things like that. If hydrogen becomes cheaper, much cheaper, I talked very quickly about colors of hydrogen, gray hydrogen, methane. My wife said, "You never explained what gray hydrogen was." And she said, "Yes, I did." Anyway, so white hydrogen or natural hydrogen, if that becomes a reality, that's fantastic, as long as it doesn't leak. So we need to, and we can't use mass specs, I don't think, mass spectrometers. Mm-hmm. Your readership are physicists, I hope, or at least, okay, so good. You can miniaturize.
This is episode number 250. They are nearly
okay.
At least graduate level.
And so, I'm looking at all this stuff. I've, for the last 20, 25 years, began to look at, what's happening to the oceans, what's happening to the currents, that the conveyor belt current is weakening the return of the Gulf Stream back to Antarctica. It's shallower, it's warmer, it's melting the grounding line of the glaciers in Antarctica. And this grounding line is melting and it begins to move. In some of the glaciers, 1 kilometer per year. Once you start this going, it's like a slow-moving avalanche. The only way you can stop it is to get colder. So we can't even maintain status quo because this has started. And this is a problem. Okay, so going back to your question in energy and what's going to happen in the next 10 years, so I see some good things. Europe is motivated. The population wants to do the right thing, willing to pay more money, but not too much more. United States produces fossil fuel. We've become, I think, the biggest exporter of fossil fuel, liquefied natural gas, and even some oil. Okay? Okay, it's about money. If you're going to make money, you want to turn off making trillions of dollars. So it's headwinds. Okay, so it needs a little bit more political will. The only thing that will give it political will is people realize the problem. I mentioned that the bottom of the ocean is very cold. Average 3.7 kilometers deep, 2 degrees centigrade. It's not Antarctica that was the inertia. It's the ocean. They got that wrong. See, the people who think quantitatively are physicists. You got an idea, you put a number behind it. Someone mentioned, you can change the ocean currents and will help, right? And you can use the ocean currents to cool it down. The scale of energy is just crazy. I don't think many of the oceanographers actually know about the Argo floats. Those are these floats. They're a little bit bigger than a person, about the same size as a person, cylindrical thing. Surface down 2 kilometers back. Temperature, salinity. It was those Argo floats, 1 per degree around the world, that we were realizing the conveyor belts are weakening and things like that. There's a new generation of Argo floats that can go down to 4 kilometers. Okay, and they're battery powered. And after, I don't know, something like 8 years, the battery runs out. The batteries have gotten better. All good news. And so you get and it wasn't until those Argo floats that we started to figure out what the ocean is doing. There was an article put in. Energy coming, hitting from the sun to Earth, there's a solar cycle. But you average over solar cycles, it's the same. Okay? Energy going out less, because there's a greenhouse gas effect. Where was the energy going? It didn't match the temperature. It's going in the ocean. So those Argo floats are telling us how much energy. Most of it goes into the ocean because you're just warming up a bunch of ice cubes. Okay? So the time it takes, the ocean current mixing, we know. We measure this, and that's why I said 50 years. Like you're smoking cigarettes for 20 years, and you're starting all these progressive mutations that will eventually give you heart disease, stroke, lung cancer, COPD. You stop smoking. And 20 years later, 30 years later, you have lung cancer. Okay? So what we have already done is not visible and will not be for 50 years.
Mm-hmm. So I want to end on a positive note.
Oh, really?
Before we are running out of time, and before we started recording, you told me about your students, how successful they are, and you mentioned a couple of times that this is now an engineering problem, so there are a lot of difficult problems to solve. How would you motivate young listeners that pick a problem to tackle and you can solve it in maybe not a year or two, but in 2 decades, 3 decades? So how to motivate young people?
Well, this problem, I would say, over the long term, hundreds, 1,000 years, long term, is the most pressing problem that science and technology and engineering has to solve. And someone mentioned there's no silver bullet, there's lots of silver BBs. This is true. There are many things. Everything counts because the problem is immense. And it's going to take a half a century, 3/4 of a century to turn the ship. But we're on the ship. And so we have to start. Since I was Secretary of Energy, during the time I was Secretary of Energy, I got a much deeper understanding of what drives adoption and all these things and wide-scale deployment. It's all about money. How do you encourage it? Well, there are some policy things. I think there should be a policy that encourages wood laminate buildings to be built from cultivated forests to replace steel and concrete. With hydrogen, we use a form of coal called coke to change the chemical form of iron to the coking process to make steel. You can get rid of that. With hydrogen, if you can have clean hydrogen, you replace coal or natural gas for industrial heat. Industrial heat is the cheapest form of energy, but it's carbon emitting. Mm-hmm. It's coal and natural gas. And but we need hydrogen to be cheap. And right now, green hydrogen made from electrolysis from wind or solar or hydro is way too expensive. And so I pick my problems now. I started in high energy physics. My thesis and postdoctoral work was testing Weinberg-Schlam-Glasgow unification. Okay, and then I started drifting, and then I did positronium, E+, E-, precision spectroscopy, part per billion. It was the best test of CPT violation in the world. Okay, then I started doing laser cooling and trapping. My thesis advisor said, "This is terrible. You're too smart. You should concentrate on only the most fundamental basic physics. Laser cooling and trapping, that's just applied quantum mechanics." But it turned out to be very useful. I only knew about making the atomic clocks. I made the first atomic fountain clock, made the first frequency reference, cesium. But it's much more useful than that. It's revolutionary many-body physics, blah, blah, new life. Okay. So I got into Secretary of Energy. So I think, okay, all these problems, how to make better batteries, how to capture carbon, unsolved problems, how to do this, how to do that. So then I said, okay. My advisors passed away. I think in the end he realized, number one, that laser cooling trapping was useful, that I went into biology in the early 1991, 92, by 1998, 99, mostly biology and polymer science. Okay, and many methods that are widely adopted. I think the work I've done in biology and polymers is as good as the laser cooling trapping in terms of scientific stuff. But now I say, okay, I've got to use my brains or any imagination or luck to solve these problems, because these are the most pressing problems society faces. I once said, cancer is terrible. We all have family and friends who've died of cancer, but life will go on. Now, if we go up to 3 degrees, 3.5 degrees, it's not an existential threat to the world polar bears made it the last warm period. But what will happen is that society might collapse. Because once you have more failed economies and countries, people get desperate. And I mentioned, 10 million, 20 million refugees around the world going to other countries, they're desperate. 200 million, the political systems might crash and burn. Already, the political systems have become very more conservative, far right. AfD in Germany, this is the Hitler Party. It's coming back to life. Why? Because they're foreigners. They don't look like us. And then some of them, when they go into the country, they're immigrants. Their parents are fine, but their kids, are growing up in slums, and they're doing crime and drugs and things. And so this political reaction is terrible. And 2 million refugees, there will be political instability in the world. And so you need to do something about it. Long before sea level rise, you'll have failed agriculture. Failed agriculture means you're desperate. You can no longer make a living in your home country. So I said, okay, time for me to be an engineer. Mm-hmm. So I'm engineering better batteries. I'm engineering ways of capturing carbon dioxide to get rid of most of the energy penalty. We're about to submit a paper. I'm very excited about this. And that could make it practical.
So it's the most important mission right now.
Yeah, absolutely.
So I think you brought to our young listeners inspiration, at least for courage to tackle difficult issues, because, no one else will solve this for us. So
we heard lots of talks yesterday about how important it is that your heart and your mind have to do something, and you must do this, you must do that. And Jane Goldberg talked about lithium is polluting, and this is horrible, and what we're doing to the earth is terrible, and extinction rates are going up. Okay? So I'm just a physicist. And so I think, okay, let's not talk about it. Let's find the solutions. The solutions have to be economical. They have to be economically competitive. So the oil and gas age will come to an end because we have better, cheaper solutions.
So let's hope for it and enjoy the rest of STARMUS. Thank you for your time, and maybe see you next year.
All right, maybe, I don't know. I don't think they're going to have to decide what they're going to do about me. I didn't show equations, but I did talk about science. And it reminds me of the story. They're preparing Ronald Reagan for a press conference. And he said, be prepared. They're going to ask you tough questions. And Reagan says, will there be math? It's a joke.
No a týmto sa náš čas naplnil, ako som povedal v úvode. Ak máte problémy s angličtinou, a neviem, čo ste teraz hodinu počúvali, tak na YouTube si môžete pustiť titulky, ktoré, keď sme skúšali, fungovali celkom rozumne. No a ešte nás čaká zo pár STARMUSových epizód, nechajte sa prekvapiť, kto to všetko bude. No a čo povedať na záver, viete, kde nás všade nájdete, kde nás máte počúvať, môžete nás počúvať napríklad aj cez apku Vedátorskú. Nedávno vyšli naše rozhovory o vesmíre ako knižka, tiež sa dá všelikde objednávať a na leto chystáme niekoľko akcií, takže sledujte, všetko bude buď v apke alebo u nás na sociálnych sieťach. No a to už z našej strany na dnes všetko. Majte sa pekne.
Existuje Boh, ak je na svete toľko utrpenia?
Je environmentalizmus nové náboženstvo?
Je lepšie nespravodlivosť znášať, ako ju konať? Ja som Jakub Betinský.
A ja Andrej Zeman.
A spolu tvoríme pravidelnú dávku.
Vzdelávací podcast pre zvedochtivých, ktorý vás rozrozmýšľa nad aktuálnymi a nadčasovými otázkami filozofie, vedy a náboženstva.
Vychádzame každý útorok, nájdete nás na pravidelnadavka.sk, Facebooku a Instagrame a tiež na denníku SME.
Tešíme sa na vás.